Resonance, interference, and beats. Here are your priming questions. The vibration of one object can force another object to vibrate. The energy can transfer. So, for example, a guitar string sets the whole sounding board of the guitar into vibration through the use of that bridge, the plastic nut that's used at the end. And that's why it's important, because that is what transfers that vibration to the sounding board. So the sounding board, the reason why it's able to make a louder sound is because rather than just having the strings vibrate, you cause the whole sounding board to vibrate, which has a much larger surface area, and that whole surface area is set into vibration, which stimulates the air molecules into vibration, which makes for a louder sound. And this is important for all stringed instruments, for things like the viola, for the cello, for the bass. The bridge itself is one of the most important aspects of that instrument because it's what transfers the vibration from the string to the sounding board of the instrument. Now, every object has a natural frequency. So when it's disturbed, it will vibrate at its own unique frequency, and that depends on the elasticity and shape of the object, the material itself, and this requires a certain amount of energy. So if you think of the glass harp, so when you fill up certain crystal glasses with water and you rub your finger over them, when you cause it to resonate, you're giving it a certain amount of energy, and it begins to resonate at a certain frequency. You change the amount of water, or you change the shape of the glass, you change the frequency, which means you change the pitch or the tone. Now, resonance itself. This is when the forced vibration of an object matches the object's natural frequency. So, for example, as far as materials go, steel is elastic and can resonate. Putty is not elastic, it's only stretchable, and it does not resonate. So as a quick reminder, elasticity and stretchability are different. So steel can be caused to stir into resonance. Now, some quick examples. The first and easiest one is the Tacoma Narrows Bridge, which is no longer around because of this. So I'm going to skip around this video, and so you can
As you can see, this.
And so here's the Tacoma Narrows Bridge, and that's when it was starting its resonance in 1940. And what you should start to see is there was enough wind that was blowing across the bridge.
On November 7th, the bridge suddenly went into a twisting motion. The wind speed was a steady 42 miles per hour. This was enough to keep the bridge oscillating in one of its natural modes of vibration with a period of 5 seconds.
And so you can see the resonance here.
But the girders were this flexible. This is photographed at normal speed.
And ultimately,
and was afraid to come out, and he perished
there was enough
along with
energy
the bridge.
to cause the bridge to collapse. There you go. Now, some other resonance examples. If you look at the xylophone, you'll see that the musician hits the pads on top, those either metal or wooden blocks, typically wooden in most cases, and there are metal pipes underneath each of these wooden blocks. Those metal pipes are resonators, and what happens is as you strike one of the wooden blocks, it creates a tone that matches the natural resonant frequency of each of these tubes, causing the tube to go into resonance and creating a larger sound. Okay, so that's for music. Another quick example is in terms of electricity. If any of you have a Sonicare or another electric toothbrush, what you should notice is that they don't have any metal conductors to charge the battery inside of the toothbrush. The way it charges is through inductance or resonant inductance, using inductors to create a resonance, and you can create wireless electricity. There are even some applications trying to do this for electric vehicles, so you don't have to plug in your electric vehicle. You can just drive over a mat, and through resonance, you can charge the batteries. That's still a very new technology, though. So, interference. This is caused by the overlap of multiple waves. So think back to the Slinky lab. When you had multiple waves overlapping on each other, you had interference. You have constructive and destructive interference. And this can happen with sound. So remember, sound is a longitudinal wave. So if you think of what happens to the compressions, it evens out the compressions with rarefactions for destructive interference. So you have areas of no pressure. And then you can also have areas of constructive interference, which means you'll have high areas of pressure or high pressure. And so that looks like this. So here's a quick diagram. So this is what can be used for noise canceling technology. You can have something that detects the coming in sound, and then you can have a small speaker that is essentially producing the inverse wave, and it causes it to cancel out the sound. If you look at this, we have two speakers here, and the overlap of their sound will create areas of high pressure and areas of low pressure. And there is a quick virtual lab simulation that we can open up. And so here you can see a speaker, and you can see the sound wave, that's the pressure, and that's just with one. Now if you have two, you can see where it begins to overlap. It produces an interference pattern, areas of very high pressure and areas of very low pressure, so compression, rarefaction, and this is going to be an interference pattern. And depending on where you are located, it can either sound louder or it can sound softer. You'll have dead spots, and it won't sound the same wherever you are in the room. And you don't need to have two sources for this. You could simply have one, and here you see the wave reflecting off of a surface, and you can begin to see the interference pattern of the wave interfering with itself. So that's some interference with sound. Now, beat frequency. This is also what's called the tremolo effect, and this is also how you tune your instrument a lot of times, by listening for the beat frequency, because it's caused by the overlap or the interference of different frequencies. And so when you're trying to tune something to another note, you will hear the beat frequency, and once the beat frequency goes away, you know that you've tuned the instrument. And so here is a quick diagram of that. You have two different waves, and when you overlap them, the green wave is the beat frequency, and that is the constructive and destructive interference of these two waves. And so this would be the beat frequency there. And this is calculated by the difference between those two frequencies. So it's a very simple equation. So here are your priming questions again. Make sure to answer these for class.